Now, one of the things that we can do with regard to a polynomial function is talk about the zeros. And that opens up a very large conversation that we can have about the graph of a function, how it relates to zeros, how x-intercepts are related also. So let's start this conversation by looking at a warm-up. In this warm-up, our goal is to solve this equation. Now, with a quadratic equation, our first line of attack would be to see if we could factor this. So 2x squared minus 5x minus 3 is going to factor into something times something equals 0. So at least that's the hope. Otherwise, we'll use the quadratic formula. 2x squared can be broken up as x and 2x, and then negative 3, the signs will be opposite. So let's try minus and plus, and let's try 3 and 1 like this, and you'll notice that if we check the outer and the inner, we get negative 6x and positive x, and so that would give us our negative 5x in the middle. So it does indeed factor into these two quantities. So now we can set each factor equal to 0, so x minus 3 equals 0, or 2x plus 1 equals 0, and so x equals 3, or x equals negative 1/2. So now, having solved that equation, let's move on to the second warm-up. Here we have a function, f of x equals 2x squared minus 5x minus 3. You'll note the similarities between this function and the left-hand side of this equation. Now, to find x-intercepts, what do? We let y equal 0, which means that we're going to look at the equation 2x squared minus 5x minus 3 equals 0. So if we do that, notice we've already solved this. Our x-intercepts are x equals 3 and negative 1/2. So you'll notice that if we factor our 2x squared minus 5x minus 3, the factors correspond to x-intercepts. Notice one other thing that this means. If we take 3 and we substitute it in for x, the output will be 0. Likewise, negative 1/2 substituted in for x would yield 0 as an output. This brings us to the definition of something called the real zero of a function. A zero of a function, or a real zero of a function, is a real number that when substituted in for our independent variable yields 0 as an output. From the warm-up and this definition, then we know that there are some corresponding statements that are related. So if r is a zero of a function, a real zero of a function, then that means that r is an x-intercept of the function. And then also, x minus r is a factor of the function. And if we solve the equation f of x equals 0, then r is a real solution. So if we want to find the real zeros of this function, then what we can do is we can try to factor it, and then our next step will be to look at how the zeros correspond to the x-intercepts on the graph. So let's go ahead and factor this. X cubed minus 4x squared minus 25x plus 100. This is 4 terms, so let's group the first 2 terms. And then plus, and we'll group the last 2 terms. Out of the first grouping, we can factor out an x squared, and we are left with x minus 4. Out of the second grouping, we can factor out a negative 25, and again we are left with x minus 4. From this, we have x minus 4 that's common to both, and we are left with x squared minus 25 whenever we factor out x minus 4. So x minus 4 is getting factored out as a common factor. Now we can factor further, because x squared minus 25 is the difference of squares. So now we know from the previous theorem that if x minus r is a factor, then x equals r is a solution of the equation, or x equals r is a 0. So we know that our answer is x equals 4, negative 5, and 5. So 4, negative 5, positive 5. Now let's look at how the graph relates to these zeros. So 4, negative 5, and 5. So if we look, we have x equals 4, x equals negative 5, and x equals positive 5. So we see the x-intercepts correspond to our real zeros. Now let's take a look at our next function. Here we can factor out an x, and that leaves us x squared plus 6x plus 9. And x squared plus 6x plus 9 is a perfect square trinomial, so it factors into x plus 3 quantity squared. So this means if we look at each factor, we have x and we have x plus 3. So x would yield x equals 0, and x plus 3 would yield x equals negative 3. Now the question that we have next is, what about this 2? What's this 2 mean? And it turns out we will call that 2 the multiplicity of negative 3. So in other words, x plus 3 was a factor to a power 2, means that whenever we solve x plus 3 equals 0, we would have 2 of those factors. So we got negative 3 twice. So that's the multiplicity of 2. And we'll talk more about that in a moment. But notice, the multiplicity corresponds to how many times we obtained that solution. So x equals 0 is a 0, x equals negative 3 is a 0, but we get that negative 3 twice. So let's take a look at the graph. So x equals 0, and then x equals negative 3. But notice, the multiplicity was 2. So look what happens at our graph, as opposed to what we saw in the previous one. In this example, we only touch. Now why is that? So whenever we have a factor, x minus r, and it's raised to a power m, then x equals r is the 0, and the multiplicity is m. Whenever the multiplicity is even, like what we saw in the last example, then our graph just touches the x-axis at r. It will not cross. If m is odd, then it will cross the x-axis at that corresponding x-intercept. So here we are given the zeros of a function and we are told the degree. So let's go ahead and write the polynomial function that has those corresponding zeros. Maybe a good way to do this is every 0 corresponds to a factor. So if we have a 0 of negative 3, the corresponding factor would be x plus 3. If 3 is a 0, then x minus 3 would be a factor. And if 5 is a 0, then we would have x minus 5. So f of x would equal x plus 3, x minus 3, x minus 5. Now if you notice, if we multiply this out, the degree would be 3. So here we have a very similar example. So let's start out the same way. We have zeros and we have factors that correspond to those zeros. So we have negative 2, we have 1, and we have 3. Now, the factor that's associated with negative 2 would be x plus 2. What's the multiplicity do? It's going to raise that to the second power since the multiplicity is 2. Likewise, 1 has a corresponding factor of x minus 1. The multiplicity is 2. and then we have x minus 3, and now that means that our function is going to be f of x equals, I can multiply the factors together, x plus 2, quantity squared, x minus 1, quantity squared, times x minus 3. But notice we have this additional stipulation of negative 1 comma 64 being on the graph. We've already taken care of the degree because x squared times x would be x to the 5th. So the degree is fine. I can multiply this whole function by a, and it will not change any of those x-intercepts or zeros. But now we need to find the a that will guarantee that negative 164 is on the graph. So f of negative 1 would be a times negative 1 plus 2, quantity squared, times negative 1 minus 1, quantity squared, negative 1 minus 3. So this would be a times negative 1 plus 2 is 1. We'd have negative 2 squared and negative 4. So this gives us 4 times negative 4 would be negative 16a. But this is supposed to have an output for negative 1 of 64. So this is supposed to equal 64. So this means that a must equal negative 4. Therefore, f of x equals negative 4. We'll replace a, then we have x plus 2, quantity squared, x minus 1, quantity squared, x minus 3. Now, we can do something very similar here. We have an x-intercept of negative 3, and we have an x-intercept of 5. So those correspond to zeros. And each zero will have a corresponding factor. So an x-intercept of negative 3 means that we have a 0 of negative 3. 5 is a 0 because 5 is an x-intercept. Now, negative 3 corresponds to a factor of x plus 3, and then 5 is going to yield x minus 5 as a factor. But notice, negative 3 recross, so I could have any odd multiplicity. So I'll just choose a multiplicity of 1 to make things simple. 5 is an x-intercept where we touch, we don't cross, so we need an even multiplicity, and I can choose any even multiplicity. So I'll just choose 2 to make it simple. And then we additionally have a point on the graph that's easily seen. The y-intercept is 0, 3. So f of x is going to be a times x plus 3 times x minus 5 quantity squared. But we need to figure out what a is. So since f of 0 needs to be 3, let's put 0 in. 0 plus 3, 0 minus 5, and this yields for us 3 times 25 is 75. A. So what's this mean? 75a is supposed to be the output whenever we put in 0, but that's also supposed to be 3. So 75a needs to be 3. So this means that a equals 1/25. So therefore, f of x equals 1/25 x plus 3 times x minus 5 quantity squared.